Hello. In this lesson, we are going to circle back to exponential functions in the real world. Our objective for our time together is to solve for unknown exponents, also known as input values, in exponential modeling problems. We're going to do this two ways: graphically using the graphing calculator and algebraically using logs. Let's revisit our elk population. In this scenario, a population of 300 elk is released into a wildlife preserve. Every year, the population grows by 12%. How long will it take for the population of elk to exceed 1,000? We can look at this situation three ways: in table form, graphically, or algebraically. In table form, we notice that in year 10, the population is below 1,000, but by year 11, the population exceeds 1,000. The table tells us that sometime between years 10 and 11, this change happens, but not exactly when. We can find the exact value graphically and algebraically. Mrs. King is going to show you how to find the exact value graphically using your graphing calculator. And Ms. Daniels, myself, will show you how to do this algebraically using logs.
Hi. So on the last screen, we saw a table of values that represented the inputs and outputs for our ELK problem and a Desmos graph that helped us find the solution. I am going to show you how to graph this function or this inequality on your graphing calculator. If you want to, take your calculator out and work along with me. So I'm going to go to my y equals screen. And in y1, I'm going to type in the function 300 times 1.12 raised to the x. That's my exponential function. And then I go down to y2. And in y2, I'm looking for the intersection between my exponential function and my linear function, y equals 1,000. And then I'm going to go, before I actually go ahead and graph these, I'm going to go to my window of values. And most calculators are set so the window is in a standard window from -10 to 10. But I'm going to change those values because we were looking for our output to be 1,000. And if you look back on the previous slide, you see that at year 10, our output is 931.75. And year 11, the population is 1,042.6. And we were looking for a value between those two values. So my x of maximum of 10 really isn't going to be enough for that point of intersection to be on my screen. So I'm going to change my y maximum value to be just 15. Anything more, anything around 11 would be okay, but I want to make sure I could see it on my screen. I have a y minimum value is -10. A y maximum value of 10 again wouldn't be appropriate. So I'm going to put, I know it has to be more than 1,000. And I'm just going to change it, I don't know, to 1,500. And if these values don't work, if the point of intersection when I go ahead and try to graph these functions is not on my window of my calculator screen, this is where I would come back and edit these values. So I'm going to go ahead and hit graph. There's my exponential function, which is in blue, and my linear function, which is in red. And I'm looking for this point of intersection of my two functions. So now I'm going to go back to my calculator's trace, but I'm going to hit second and then trace, and it will take me to the calculate screen. And I am looking for the intersection. So I hit enter, 5 intersection, and it says, do you want the intersection of your first function y1? And we do, with, we hit enter to say yes, with my second function y2, and I hit yes. And the reason why it asks you which functions you're looking for the intersection for is because you can have more than two functions in your y equals screen on your calculator. We just happen to have two, so that makes it a little easier for us. I hit enter. I really don't want to guess. I really want it to do the work for me. Hit enter again, and it gives me the intersection of my two functions, 10.623725, which is the number between 10 and 11, which is what we're expecting. And this tells me that it's 10.623725 years that it will take in order for the elk population to equal 1,000. So any value greater than that X value is when the elk population would be greater than 1,000. So I hope this was helpful.
Now we want to know when the population of elk at time X exceeds 1,000. How do we solve for an unknown exponent, which is not easy to guess and check? This is why we need logs. Now let's solve this algebraically. The first step is to replace p of x with 1,000 because we're looking to find at what time the population exceeds 1,000. The next step in the process is to isolate the exponential term, in this case 1.12 to the x power, by dividing both sides by 300. That gives us 3 1/3 is less than 1.12 to the x power. The next step in the process is to rewrite this exponential inequality using logs. Log base 1.12 of 3 1/3 is less than x. Finally, we evaluate the logarithmic expression and find that 10.6236 is less than x, which tells us that after 10.62 years, the population of elk exceeds 1,000. This confirms what we found graphically. In summary, when you're trying to find the input value or unknown exponent of an exponential function, one that you cannot easily guess, you can either solve graphically using technology by setting up two equations and finding the point of intersection, or solve algebraically using logarithms. Now it's time for you to show what you've learned. There are 3 application exercises for you to complete in Google Classroom. And remember, we are here to support you. Please attend office hours, email your teacher, or partner with a classmate. Have fun with this activity, and we'll see you next week.